welcome to Old Spiral Podcast. Brian, how are you doing today on this nice spring day?
It was a nice spring day. We got a nice spring shower right in the middle of it.
We did.
I worked outside, worked on the chicken coop a little bit. I worked on the last few things I need to finish up for my schooling. So I graded my last statics assignment. That felt pretty good to get that over with. Still have to watch and do a report on a couple seminars. And then, of course, why we're here today, I have to give an 45-minute presentation on Wednesday to talk about all the research I've done the last couple years. And then a committee of 3 will decide whether or not I get to graduate.
Right. And you're under sort of unusual circumstances given the COVID-19 epidemic. You now have to defend your thesis via Zoom. Is that correct?
That is correct. So I had a meeting with my advisor last Wednesday or something, and my power went out.
Oh.
I think it was Friday. And my power went out, and then I tried to use my phone as a hotspot, and it did not really work.
Oh.
So hopefully my power remains on Wednesday yeah. Because that could be shitty.
Well, there it is. So what are we going to talk about? What is your thesis over?
Well, we're going to talk today about a compound called nitrogen trichloride. It's as it sounds. You got one nitrogen attached to 3 chlorine atoms, and it exists inside indoor pool air.
Okay. So this is going to be pretty pertinent information if you happen to have an indoor pool, and maybe some best practices that you could start applying to how you maintain your pool.
As far as best practices go, I think that if I can convince you of anything today, don't pee in the pool.
Oh, man.
And I'll admit it right now. Before I started this research, I was an offender. I did not, who wants to get up soaking wet, walk to a bathroom, pull down your wet trunks? I'll stop there. But I'm just saying, I may or may not have been an offender on the whole peeing in the pool thing. But I'm telling you right now, that ended after I started learning about nitrogen trichloride and just. It's what happens in the pool doesn't stay in the pool. Nitrogen trichloride especially, it goes into the air really readily. And then if you are someone who spends a lot of time in indoor pools, that's why it's a bigger deal in indoor pools because the air kind of builds up. So if you don't have a good HVAC system, outdoor pools, you got a good breeze, it's not going to build up as much.
So what is the detriment or the harm that could be done to somebody from breathing in this? Yeah,
and I'll get into that. If you're listening as a podcast, I'll try to be as descriptive as possible. We won't get too technical. Drew's here to keep me from spouting off chemical names without regard for the common listener. But what we're trying to do, what I'm doing right now is I have a PowerPoint presentation. I'm recording it. And so I'm going to get that uploaded to YouTube. So if you want to, stop right now and head over to YouTube. You can kind of follow along with us.
Or if you happen to be a graduate student that is interested in the same measurement that Brian used here, you can study up on that YouTube video.
Exactly. Okay, but the health effects of nitrogen trichloride. I'll start out with an anecdotal story. Why not? Kind of fun.
All right.
I have a friend. Her name is Amelia. Hello, Amelia. She was a swimmer as a child, and she was swimming at a meet one time, and she was swimming. All of a sudden, out of nowhere, she had an asthma attack, right? Hard time breathing, had to get out of the pool, had to get some fresh air, all this stuff. And so that's one of the things that nitrogen trichloride can do is trigger asthma attacks, right? It can also cause eye irritation, throat irritation, in extreme cases, vomiting. So those are all the short-term effects. And those are pretty well known. And there's been a lot of research, which we'll talk about a little bit, about what levels that starts occurring. But there are some long-term effects that are suspected, although more epidemiological studies and just kind of a fine-tuning of actually measuring these compounds in pool air will need to be done before we can definitively say bladder cancer and long-term bronchial hypersensitivity is going to occur if you're exposed to this for a long time.
Wow.
Another short anecdote, a couple people who were elite swimmers in their youth, now their kids are growing up and swimming, but they can't stay in an indoor pool for more than like 10 minutes before they have to go get air because it just gets sore and hard to breathe and stuff. So it's not a good compound. And as we alluded to earlier, peeing in the pool tends to make a lot of this compound. Urea, found in urine, it's one of the... it's a really good precursor for this compound. The other stuff that makes this compound would be sweat. You're in the pool, you're exercising hard, you're sweating, you're going to create some. Don't feel bad about that. That's just going to happen. And then the other big thing besides peeing in the pool, shower before you get in the pool. I always thought, well, I took a shower this morning or before I came, I'm pretty clean. No, just still rinse off. One study I was looking at found that if you shower for a minute, and that's just no soap, you're just water over your body, kind of rubbing it for a minute, you'll leave half the amount of pollutants in the pool as if you didn't shower.
Wow.
Rinse off, yeah.
And so I would imagine it's equally as important, obviously, to shower after you swim as well.
Yeah, of course. That's not something I looked at too much, was how chlorine affects your skin and all that stuff. But yeah, it's good to shower when you're done in the pool.
Yeah.
Yeah. And plus, you don't know who else has been in the pool. And
who else has peed in the pool?
Exactly. So nitrogen trichloride, it's a class of something called a disinfection byproduct, which, simple enough, right? You put chlorine in the pool to disinfect. It's called free chlorine, and it eats up all the bacteria, dirt, sweat, urine that you put in the pool, and it creates a whole bunch of compounds. For those chemists listening, we get trihalomethanes, haloacetic acids, haloacetonitrile, and chloramines, which nitrogen trichloride is a chloramine. Ammonia. Everyone's heard of ammonia, right? Mm-hmm. NH3. Okay, so nitrogen, 3 hydrogens. You take off one, you put on a chlorine. That's nitrogen monochloride. You take off another hydrogen, and you put on a chlorine. You get nitrogen dichloride or dichloramine. And then you take off that third hydrogen, put on a third chlorine, and you got nitrogen trichloride. So these are all compounds. Trihalomethane, that the most abundant one found in the pool would be chloroform.
Oh, really?
Yeah, chloroform is it's a chlorine. So if you got chlorine, it's a carbon. So methane, right? Carbon, 4 hydrogens on it, and chloroform is if you took 3 of those hydrogens and put chlorines in their place.
So how much of chloroform particulate matter is kind of hanging out in the air that you're breathing in while you're swimming? Is it quite a bit, or?
It's not horrible. I've only found one study. I'm sure there are others, but I only looked at one study that said that they were in an indoor pool, found around 20 parts per billion. Let's see. I should get some good references for where it's found other places, but it's not super high. It's not standing out to me as something dangerous or anything.
Gotcha.
Yeah, I'm sure you can find comparable levels in the air we're breathing now inside homes. But That's a story for another day. Someone graduated last semester, and he did a study on some of these compounds in indoor air. And it's actually pretty surprising. Side note, open your windows once in a while. Very good, very important.
I recommend, 30 minutes a day?
Yeah.
Something like that?
There's always a window cracked in my house somewhere.
Yeah.
Yeah, just after studying all this stuff. You asked earlier, chlorine, liquid, solid? Who knows?
I don't really know much about pool maintenance. Maybe you could go into that. What sort of additives, what are my choices if I'm putting chlorine into my pool?
Sure. So, it sounds silly. Bleach, right? That's a chlorine-containing compound. A sodium hypochlorite is kind of that active ingredient in bleach. That can be used in a pool. That would be liquid. Mm-hmm. And then there are solid ones, or granular solid. Sometimes they'll come in little pucks. Sometimes they'll just be in a granular mixture. And that one, you're looking at something called either calcium hypochlorite. And then a lot of these things have stuff in them. They're trade named dichlor and trichlor, which sounds pretty badass. But basically, those just have an additive, especially for outdoor pools. It keeps the UV light from eating up your free chlorine as quickly.
Oh, sure. Yeah, that's something to consider, UV versus indoor and outdoor. I didn't even consider that. Huh.
Right. And it was kind of neat. I don't think we'll actually get into it in this, but I took a little UV light sensor to the WSU pool, which, well, by the way, I took measurements at a WSU indoor pool. Mm-hmm. I took the UV measurements outside and inside, and it's ton of windows at the WSU pool. And they just have this UV coating, and so outside you'd see like 29 units. I can't remember what it was offhand. And then indoor you'd see like 0.5. So it was cutting out almost all UV light. And UV light, though, also, besides giving you skin cancer, it will break apart these nitrogen trichloride atoms. So maybe a little sunlight getting in the pool, a little UV light can reduce those levels a bit. But that is me speculating. If you put liquid chlorine in the pool, if you put solid chlorine in the pool, what they're going to do is, or you put gaseous. A lot of people will use chlorine gas to chlorinate pools, especially really large pools.
It's pumped in?
It's pumped in and usually to the bottom of the pool.
Oh, wow.
Yeah, and it just kind of bubbles through and gets into solution.
So let's say I do a cannonball and I end up down there by the pump. Is that going to be...
Nah, it's not a big deal. They got it figured out. Again, I don't know a whole lot about the actual equipment, but you'll be fine. All right. The chlorine gas, I think it's generally used for larger pools. And then you can dissolve a gas into a liquid just like you could dissolve a solid into a liquid. So that's what's going on there. So no matter what form you put in, right, you're going to get two things. At a pool pH, which if you want a pool, your pool pH should be between 7.2 and 7.8. And at that pH level, you're going to get something called hypochlorous acid, HOCl, and hypochlorite ion, OCl. So it's missing the H. It's got a little bit of a negative charge. And basically the HOCl is going to be the better sanitizer. It's more readily, it's going to oxidize these compounds and create the disinfection byproducts. So that's kind of the whole idea is you're putting these, so you got a pool, no one's been in it, you got water, you put in a bunch of chlorine, and you're going to get water, hypochlorous acid, and hypochlorite ion all swimming around in there, waiting for your dirty body to get in, so it's got a job to do.
Or your pee.
Or your pee. Yeah, exactly. So yeah, after you get in the pool, it makes these compounds. We've got nitrogen mono, di, trichloride. We just talked about those a minute ago. It'll make more sense again if you're following along. I'm referencing some slides here. So I didn't measure anything that had to do with pool water. My background, so my master's degree is going to be in something called environmental engineering. And basically what environmental engineers do is it spans concrete, all right? It spans water, so wastewater or drinking water, and land, so you could be a soil engineer, and then air, right? So water, land, air. I got a bachelor's degree from LCSE, right, in chemistry, and under Nancy Johnston, and she works there. She was trained as an atmospheric chemist, so that's what I consider myself as, more than an engineer, because I never really took engineering courses. I've taken a few now, but I consider myself an atmospheric chemist. So I'm concerned about what's in the air.
Right.
And let's see here. Nancy Johnston, I'll get another side note. She studied under the gentleman at UC Berkeley who discovered what caused the hole in the ozone layer
Right. Yeah,
back in the day.
Pretty impressive accolades.
Yeah, it's pretty cool. That was her advisor in grad school when she was getting her doctorate.
Right.
And that's pretty cool.
Yeah. There's quite a extensive catalog of really impressive work that many of the professors have done at LC, and hopefully we can have some of those folks on and discuss some of the things they've studied, because there are a lot of really cool things that many of the professors have done.
Yeah, don't let me forget. Nancy's putting out a paper with some of the research that I did and many other students when I was at LCSC. And if that gets published, and even if it doesn't, we'll have to have her in just to talk about all that. We're measuring sulfur and a whole bunch of some carcinogenic
here
compounds
in the valley,
in
right?
the valley.
Yeah.
So that'd be kind of cool to know what's in that air. But back to pool air. Nitrogen trichloride, there's something called a Henry's Law coefficient. Basically, what Henry's Law describes is how soluble a gas is in water. I think it can do other mediums too besides water, but we're focused on water. So if you are watching, nitrogen trichloride's coefficient is 0.1. Or what's that matter? Doesn't matter. We go look at all the way up to monochloramine, and it's up to 94, right? So 94 to 0.1, so it's like 1,000 times bigger.
Right.
And basically, the smaller the number, the less soluble it is in water. So what's happening is you get in the pool, you make all these disinfection byproducts, and nitrogen trichloride is very volatile, is what we'll call it. So it escapes from water really quickly. And so the rest of them, they'll get into the air a bit, but they're mostly going to stay in the water. And nitrogen trichloride is going to leave the water as fast as it can and get into the air, where we breathe it in, and it causes all these health problems. And so that's where I come in with wanting to measure nitrogen trichloride. So before we get to what I did, from the research that I've done, chloramines in water has been going back it's been studied for quite a while, because one of the steps in wastewater treatment, one of the end steps, is either using UV or chlorine to disinfect it before it goes back to the river. And so these disinfection byproducts are also made in wastewater treatment, and the chloramines and all that stuff. And monochloramine is sometimes added to drinking water before it leaves the pump station. It helps it stay sanitized from the pump station to your house. So that's been looked at for a long time, but as far as nitrogen trichloride in pool air, it's only really been looked at since maybe the 80s, and the scientific paper that is cited most often, the people that developed the current, accepted, quote-unquote, method for measuring nitrogen trichloride was done in 1995 in France.
Yeah, I was going to say, and wasn't a good chunk of the research that you've discussed with me about in your what you reference in your research, wasn't that from Europe? A lot of it?
Oh yeah, definitely.
Wasn't there a paper from Czechoslovakia or the Czech Republic or something like that?
The guy's name was Czech.
That's what it was.
Yeah. Yeah. I don't remember where he was from. A lot of it's from France, Switzerland, Norway. I've got a table coming up it'll show. I think it's probably the next slide. To show all. It was a really big table. I shortened it up to the past few years, but it hasn't really been measured in air too much. And so what we have found is it ranges from about anywhere from undetectable, which we're talking 3 to 10 parts per billion, if not lower, to over 350 parts per billion. Is the highest level that I was able to find in the literature. We'll just jump to this table really quick. So as we can see, there's countries: France, Germany, Sweden, Canada, France, Norway, and then there's one lab in Purdue that has been studying chloramines, and then even they only have a few actual tests where they measured the air. Like I said, they do a lot of water stuff. where
And
they
that's
actually,
again probably relating to wastewater treatment, not so much pools.
no,
at the
no, they
Purdue lab?
measured it in the pool area.
Oh, it was in
yeah,
pools.
but even that lab from Purdue, there's got to be less than 500 U.S. measurements of nitrogen trichloride
Wow.
in pool air. And my measurement technique, which we'll get into, I was able to get in 13 days at the pool a little over 11,000 data points for nitrogen
Wow.
trichloride, which was really cool.
And didn't you say that's at this point the highest number
far
of
as
data
I can
points?
tell.
Yeah.
Yeah, and well, so let's talk about that. That would be, oh, right.
It makes sense
Can I
that
not go backwards?
that so many of these studies have been done in colder places where there would be many indoor pools.
Yeah. Well, I skipped over some slides, and it looks like I can't go backwards for some reason. But what I'll say is the methods now. So basically, you're pumping pool air. You get this pump, and you get a filter. Well, it's a bunch of filters, right? The first ones are to keep droplets out, water droplets out. And then the second one has a special coating that takes the nitrogen trichloride and it breaks it into ammonia and hypochlorous acid. And then finally, you'll take that and you'll convert all that into chloride ions. And then you'll measure it using something called ion chromatography. Mm-hmm. And so what they get is a total amount of chloride ions. It's like, great, but I want a nitrogen trichloride. And then you just say, well, there's 3 chlorines for every nitrogen trichloride, so just divide it by 3, and that's your number, which is fine. But what if you get some dichloramine on there? Or what if you get one of these other chlorine compounds on there and it breaks apart? And how do you know you're measuring nitrogen trichloride and you're not getting an artificially high signal from some of these other things?
Gotcha.
And the thing is you don't.
Right.
I mean, even the author that came up with that's like, hey, so I'm going to recommend, people were reporting symptoms at about 50 to 100 parts per billion using this method. So that should be the limit when you're measuring it using this method. And then they say, further studies can come out and change that. And so that's something that I was trying to do at WSU.
Very cool.
Yeah.
So what sent you down this path of researching the air in and around indoor pools? How did you come up with that as part of your thesis?
Sure. Well, okay, so I met Tom, who's my advisor, my last year at LCSC. Mm-hmm. Nancy and I we were studying the air here in the valley, and so was Tom. He had a small research group composed of, I think at that time it was 2 students.
Okay.
When I came in, we had 4, and now when I'm leaving, he's only gonna have 1. But we had it was Yibo. I like Yibo Huang Fu. He moved back to China to do a postdoc when he was done. But I met them studying the air here. I applied to the WSU program. I knew I wanted to go to grad school. I didn't really know what I wanted to do, like chemistry or something else. WSU used to have an atmospheric chemistry program in their chemistry department, but years ago it got moved into the environmental engineering department.
Oh, okay.
Yeah, so they're doing kind of the same stuff. Tom has a PhD in chemistry, so he's a chemist as well. But he basically said, do you know what you want to study? I didn't really. And he kind of listed out a handful of things. And I said, well, I'll try this one that seems really interesting. I can use a lot of my chemistry knowledge, which I definitely did. And it was interesting. Would I want to stick around for another 4 years at mediocre pay and earn a doctorate in studying this? No. No, I don't think. I haven't really found anything I'd want to commit the next 4 to 5 years of my life to getting a doctorate on, so I'm just hanging up my hat at a master's.
Yeah.
No, it was his idea, sort of. I think he had heard about it. It's a really great opportunity to use the instrument. So his focus kind of is on the instrument that we use called the proton transfer reaction mass spectrometer, and one of its nice things is you take it to the place you're measuring it, and you're taking samples in real time at the site. And that's kind of like I said, the other one, you're getting these things, they break apart. You have to take it back to the lab to analyze it with this other method.
Yeah.
And you're taking a sample for 1 to 3 hours with this other method that Harry developed, the guy from France. Mm-hmm. And so if you want 10 samples, you got to do 10 laboratory experience to get. And with this thing, it's just like bam, bam, bam.
So what's the size of this device?
It's probably 2 feet wide, 3.5 feet tall, maybe 3 feet long.
Relatively small.
Yeah, it's not super big, really compact. It's got these turbo pumps in it. So, because everything's you got to suck out of all the air, get it to these really low pressures in there to make everything work. And so if it's on and you bump it really hard, it could explode because those pumps are going thousands of RPMs, you know. It's a very expensive machine, and you're not supposed to get water in it, and I got water in it like the first couple of weeks I was there, which was fine because I got to learn how to take it apart and clean it. But that's kind of how I got into it. It was an option, and I said, yeah, why not?
Very cool.
Yeah. So that's kind of there's a few things that make this research nice for an academic. One is there's very few U.S. studies. I only have found, and I could be wrong, there could be some out there, but as far as published research goes, there's only the one lab out of Purdue that I found was putting anything out in the U.S. So that's like, hey, if you want to publish a paper, you know, you have to find reasons for people to want to read it. If you're just doing something that's been done and done and done, it's really hard to get it published. But if you're like, hey, look, I'm the second person to try this, that's something. The second reason that made it really cool is I just ramped up the amount of U.S. data points of nitrogen trichloride in pool air by a factor of like 1,000.
Right.
You know what I mean?
Yeah.
And so those things combined, it was really neat. And then the way I calibrated the instrument, not only for nitrogen trichloride, but for some of these other, they're called volatile organic compounds, stuff like methanol and acetone, stuff like that. It readily evaporates. Mm-hmm. The way I calibrated the instrument for some of those, I didn't make up the whole system, but I kind of did a couple things that were new, and I haven't seen them in literature. Doesn't mean they're not there, but it was just kind of like, hey, guys, check this out. It's cheap, it's fast, and it works really well. And we'll talk about that in a minute.
Cool.
And then the third thing is, what happens, this is what we were talking about right before we started, is what happens to nitrogen trichloride when it leaves the pool?
Right.
Good luck finding anything, right? There's a bunch of information on other chlorine sources, so when it leaves the pool, it's going to get hit with sunlight, it's going to break apart into these things called radicals, and then it can lead to an increase in ozone formation. So around the oceans, you're going to get a lot of this from sea salt is going to create these chlorine radicals, and you can lead to an increase in ozone. But even in inland areas, we can see some of these chlorine compounds that are a result of this chlorine and ozone and all this stuff. And so it's just another thing that goes into the ozone cycle.
I figured that the radicals near the ocean would be largely in part from surfers getting a lot of really radical airtime. Thank you.
I love it.
Everybody's laughing. Show of hands.
I got 2 hands up.
I think all of the hands. Yeah. Okay.
Yeah, all the hands. So, are you bored yet?
Well, I'm not really ready to jump into the deep end. A la Cameron from Ferris Bueller's Day Off.
You got 4 left.
I guess I better save
I'm giving you 6 puns.
Maybe this would be a good spot for us to talk about one of our favorite local establishments.
That's right. You know what? That is a good idea. I think what we're going to do, we mocked up a commercial. It's for Hogan's Pub. You know we love Hogan's Pub. We know we love Hogan's Pub. And if Hogan's Pub is listening and you want us to run this ad on a regular basis, go ahead and send us an email at oldspiralpodcast@gmail.com. And that goes for anyone else that's a business owner that wants a little bit of airtime on Old Spiral Podcast. We'll see you in a minute. AOSP fans, just wanted to take a quick break to tell you about our favorite family-owned local bar and restaurant, Hogan's Pub. There's no better place for lunch, dinner, and hopefully returning soon, live music. Hogan's is home of the legendary Hogue sauce and the best burgers in town. Don't forget about their bite size either. Call ahead and the friendly staff will bring the order to your car, and don't forget to include a growler of your favorite local beer. Hogan's Pub. Come as you are.
And we're back, and we love Hogan's.
Yeah. I thought that was a great commercial. So let's talk about what the heck is proton transfer reaction mass spectrometry. A lot of big words. We're going to make it not actually that difficult. If you've taken high school chemistry, you may have heard of a proton. Proton has a positive charge. You sleep yet? I'm just joking. So proton has a positive charge. And so what we do is we use water vapor, H2O. We shoot a bunch of electrons at it. It does all this stuff. I'm not going to really get into too hardcore right now. But it puts a proton on there. So now it's H3O plus, right? H3O instead of H2O. And if your compound wants the protons more than water does, that compound will take that proton from water. So now it's just back to H2O again. It's nice if you're looking at the slide, you can see I've got a generic compound marked R.
Right.
And it'll just take that proton from water. And what that's able to do then is go through something called a mass spectrometer. And that is just a fancy way of saying it's charged because it goes through these magnets that kind of direct the ions where they're going. And then the detector is kind of spaced out. So just like you can imagine, if you throw a bowling ball, it's going to go a few feet and then drop. Mm-hmm. If you throw a golf ball, it's going to go a lot farther before it drops, right?
Right.
So it's kind of the same idea. Lightweight compounds are going to hit the detector at a different spot than heavyweight compounds.
Sure.
Right? And so what that allows us to do is nitrogen trichloride, it weighs 119. You throw the extra proton on there, now it weighs 120. And so we can say, detector, I want you to measure mass 120, and it will. And so generally we have a whole list of compounds, and generally I'm just going to say for shorthand, you say detector, measure each compound on the mass list for 1 second. So to measure this one, it'll be 1 second, it'll take a measurement, then it'll go to the next one for a second, and then it'll go to the next one, and we call it cycles. And what happened in the pool was mine would cycle through my mass list every 96 seconds. So I would get a nitrogen trichloride data point every 96 seconds. And same for all the other compounds, because it just cycled through that list. And so it's open for a second. For that 1 second, it will count how many times it gets hit by one of those ions. And every time it gets hit, it causes all these it causes all these electrons to get made. And then what that does is it sends a signal from the instrument to your computer, and your computer in hertz, right? Electric signal. And then you got nothing going on, and then all of a sudden you got stuff coming in, and your signal will increase. Mm-hmm. And when we calibrate the instrument, we give a known concentration to the PTRMS, and then we see where the signal goes, and we say, oh, okay, this concentration relates to this signal. And then when we go out to the pool where we don't know what the concentration is, we get a signal, and we can use that factor, the sensitivity is what it's called, to determine, oh, okay, well, if I've got this signal, that means this is the concentration.
So were there any other high measurements of things of compounds at that 120 that you detected, other than sort of what you're mainly looking at, or did anything surprise you in that?
Drew, I don't think you know how good of a question that was. Because that was a very good question. That's one of the problems with proton transfer reaction mass spectrometry, because, okay, nitrogen trichloride weighs 120. Maybe there's another compound in the air that also weighs 120.
Oh, so it's not sophisticated enough necessarily to detect. Okay,
No,
I
if they
see.
both have the same mass. But there's things we can do. You can look at things called isotopes. So inside a nucleus, you've got protons and neutrons. If the amount of protons changes, you've got a new element. If the amount of neutrons changes, it's called an isotope. Same element, but an isotope. So a common one, you've heard of carbon dating, correct?
Sure.
So carbon dating, carbon has an isotope of 16, right? So carbon generally weighs 14, but carbon 16 is a very common isotope. It's got 2 extra neutrons, so it weighs 2 more. And these isotopes, they exist in a ratio that's kind of universal. I don't remember what the carbon 16, carbon 14 isotopic ratio is what it's called is. But let's see, I'm trying to think if there's any that I do know. Nah, that's okay. But they'd exist in these certain ratios. Oh, I guess I do because we measure water vapor's isotope and we multiply it by 490. So the isotope for water vapor that we measure is, I don't think it's water vapor, I think it's something else. It doesn't matter. Is it for every 490 of the regular one, you'll get one of the isotopes.
Gotcha.
So we can look at these isotopic masses and say, oh, look, it's a 1-to-1 thing. That gives you a clue that it's what you're looking at. But yes, that's one of the difficult things about PTRMS is how do you know that mass 33 is really ethanol? It could be something else. So, very good question.
So you'd have to eventually train whatever device that you're using to recognize, or hopefully one will come out eventually that will recognize what it's actually picking up at that specific 120 measurement.
Yeah, and there are certain types of mass spectrometry and other measurement techniques that have a resolution better than 1. So some of these things you can get down to the 6th or 7th decimal place difference.
Oh, wow.
Yeah.
Okay.
And that's when you can really start picking these things apart. Yeah. But for what we did, I think it worked really well. It looked like nitrogen trichloride was the only thing we were measuring.
Okay.
So here, if you're looking, I've got a cross-section of the PTRMS. So basically, water vapor comes in. We have something called a hollow cathode ion source, shoots electrons at it. We get a whole bunch of these H3O+, and then again, the reaction we saw earlier. And then this is just kind of what it looks like. We put these are rings with a hole in the middle. That's why they look like rectangles on here. And basically, we put a charge, so it's more charge on the left side, less charge on the right side, and then these charged compounds are propelled toward these magnets here in the quadrupole mass spectrometer, and then finally they'll hit the detector.
Gotcha.
Yeah. I did all these nice things for my official presentation. Okay, so like I said, we've got to calibrate it. Okay, so take it by instrument to the pool. Great, I've got a signal. What does that signal mean? It's useless until you calibrate it. So the way people mostly calibrate it is using gas standards. So it's compressed gas in a tank with a known, usually it's around 2 ppm was the compounds we're looking at, was the concentration in the tank. And then you would dilute it with, they call it zero air because it doesn't have any of these compounds in it.
And ppm for the folks at home is parts per million, correct?
Yep. And it's parts per million. When we're talking about air, we'll usually throw a V on the end. Parts per million by volume.
Right.
And that's just basically for every million things in that packet of air, you're going to maybe see 10 or 100 or whatever. If it's 2 parts per million, every 2 for a million compounds can be that thing.
Sure.
Yeah, so really, really low concentration stuff, which is awesome.
That's good.
They call it trace components of air. But we also use these things, so not all compounds either like being in the cylinder, or maybe they really like being in the cylinder and adsorb to the walls. And there's some compounds you can't use compressed gas cylinders with. So we use these things called permeation tubes, which that's just we have a little chamber. It's set to a specific temperature, and there's this little tube, and it's got your pure compound in there, and it's got a precise hole drilled in it, and so it releases a certain mass of the compound per minute, right, at a certain temperature. And so then and then with the amount of airflow going through, you can use that mass per the airflow and say, okay, here's my concentration.
So the PTR-MS is controlling or manipulating that temperature, or just in the outside air?
Separate things. So the PTR-MS, all it does is it sits there and smells. So it's constantly taking air in, right? And then so what we'll do is we'll use all this Teflon tubing and line and different airflows to bring things to the PTR-MS.
So you have to, or you hope that you can keep a consistent temperature throughout your...
We do, and I monitor the temperature. I've got a temperature probe in there. I'm always looking at the temperature. We've got things called mass flow controllers that control your airflow, and then I have airflow measurements that I can take before and after to make sure my airflows were all consistent. So it's really good. I mean, we measure the airflows, we measure the temperatures, and even in the lab, there's something called the ideal gas law, which is very important. And basically, an equation is like a teeter-totter, right? So on one side of the teeter-totter, you've got pressure and volume. So what we're talking about there is like the atmospheric pressure. In this room, it's probably 0.95 atmospheres because we're a couple hundred feet above sea level. At sea level, you're at 1 atmosphere, right? In Pullman, we're about 9.92 atmospheres generally. But you use the pressure and volume on one side, and on the other side, you have this constant, they call it the gas constant, and you have a number of molecules and temperature, right? So if you want to keep it equal, if you increase the pressure, you also have to increase the temperature, number of particles, and stuff like that. And so we can use, like the permeation tube, to get a number. We can use the airflow to get a volume. Then we have a constant. We take the lab temperature, we take the lab pressure, and then we can get these concentrations from it.
So in addition to calibration, do you also have to clean this instrument each time you're done using it, or is it not really something that...
Not each time. We probably clean it every 6 months or so. And then, of course, we use water vapor to make these the proton transfer reaction, so we'll have to refill our water container every now and again. And we have these really, really nice water filtration systems, so you get ultra pure water.
So what other purposes would I need this particular device for measuring? What other applications would I use this for?
Well, this device is really cool. So it's nice because you can measure air. We talked about this proton affinity earlier. So water's proton affinity is about 697 kilojoules per mole, right? So nitrogen trichloride's at 721. It's pretty close. And then there are compounds like formaldehyde, which I think was something around there, in between those, and hydrogen sulfide also in between those. And so compounds with a proton affinity less than water, they're never going to take that proton from water, so we're not going to see them. And that includes chloroform, which is why I didn't measure chloroform in the pool air, but also includes nitrogen, CO2, oxygen. So when we're measuring in the air, because if it did measure those, that's all we'd see, because that's what's in the air. That's like most of what the air is.
Right.
So that's what's cool about the PTR-MS is it's blind to those compounds. It's used to measure what are called volatile organic compounds, and PTR-MSs have been used on airplanes to measure stuff way up high. They've been used in cities, urban areas, to measure like car exhaust, a lot of carcinogenic, a lot of the VOCs are carcinogenic. And so it's just an air quality measurement tool. And and what's cool about it, like I said, is it's got this almost real-time measurements. You can set it up and just leave it running for a week, a month, or whatever, and get continuous data. And then what else was I say? I don't know. It's just really cool. It can do all this stuff.
Have to be careful where you leave it because it costs so much money.
Yeah, generally it's left in a pretty secure area. When Tom had it down here, they had it at Sunset Park, kind of back behind. I think it's a water something or other, that big building up there, and they had it all gated off with a padlock inside. And then there was they called it the MACL, the Mobile Atmospheric Chemistry Lab, is this little trailer. And they had big towers up top, and they had sample tubes everywhere, and everything was locked inside that as well. Yeah, but it's been used. I don't know about I think in our lab it was used in Mexico City. That Yibo that I was talking about earlier, he looked at 10 different houses in and around Pullman, I think, and so he did indoor air quality, which is kind of a big deal now, and all that stuff. So it's very useful. So permeation tubes, gas standards, that's all fine and well, but nitrogen trichloride, you make it in water, right? So how do you get it out of the water into the air so I can measure it with the PTRMS? This is what I'm going to look at. And the dynamic dilution system, it uses a syringe pump to inject my solution, and I know what the concentration is in my solution, into the air, into this heated stainless steel tubing, where it leaves the water into the air and can be measured by the PTRMS. And that dynamic dilution system, I didn't invent it, but the way I used it, at least in our lab, it hadn't been done before, and I can't find it in literature the way that I've been using it. And it's cheap. Gas standards, these big tanks, they can cost a pretty penny. I can use a few milliliters of one of these liquid solutions, dissolve it in water, and the cost is not much.
Oh, wow.
Yeah, so it's really cheap, and it seems to work really well. Let's see, moving on. Oh, yeah, here's the proton affinities I was talking about. If you're watching along, we've got a line here that represents water, and if you're close to this line, what's going to happen is you're going to get it protonated, but also water is going to kind of take it back. There's going to be this back reaction where you're trading this proton back and forth, and it can lead to really low sensitivity. So even at high concentrations, you'll see kind of a low signal. So that, coupled with the fact that, again, if there are any chemists listening, you might have done an experiment with nitrogen triiodide, which is kind of similar to nitrogen trichloride in a way. Highly explosive compounds. The guy that discovered nitrogen trichloride, Dulong, back in, I think, the 17 or 1800s, he purified it, and it exploded, and he lost 2 fingers and an eye. Yeah.
Wow.
In water, it's safe at very, very low concentrations. So I was getting 0.002 or 0.003 moles per liter or with molarity, and it's safe to up about 0.9. So I've got these super dilute concentrations, so it's really difficult to make more than 100, maybe 200 ppb with the dynamic dilution system. And then on top of that, you've got this back reaction with water happening. And so to get a really good signal, and it's just difficult with nitrogen trichloride. And that's actually what I spent most of the time on, was just trying to figure out how I was going to do that.
Right.
And I'm skipping through a couple slides here. This is just showing theoretical, what your sensitivity should be, and then gas dynamic dilution, and then the gas standards, they agreed very well together. And then you can see, like this compound acetonitrile, its sensitivity is, I got around 18, but the theoretical says it should be about 24. There's just things that happen where you can't always use the theoretical sensitivity that you can calculate using reaction rate constants and all this stuff. What happens a lot of the time, though, is a bunch of people using PTRMS, they will report their results using this theoretical sensitivity, and it might not be as accurate as they'd like it to be.
So instead of sort of adjusting your research design or just reporting a more accurate representation. They're kind of just going off of
Yeah, well, hey, some of these compounds, they're hard to calibrate, you know?
right.
Yeah.
Kind of like we discussed earlier.
Yeah, and I don't know the whole reasons behind it. I didn't spend a lot of time reading those papers because I was really focused on the whole nitrogen trichloride thing.
Right.
But basically, so you could see this NCPS. Another way to look at that is your Hertz signal. It counts per second, right? You know, I said it's open for a certain amount of time, and it counts how many times it gets hit. That's what that CPS is. And then so it's CPS per ppb. So if you take, and I've got a signal in Hertz, and then you can divide it by Hertz by ppb, and then you're left with this parts per billion concentration. So if I have a signal of 130 for methanol, we're looking at methanol, I got a sensitivity of 13. If I have a signal of 130, I would divide it by 13, and I would say, oh, I have 10 ppb, right? Not so bad. So I think next, here's a cool slide. This is one of my favorites. So this is we've got a diagram of the dynamic dilution system. You can hook gas standards up to it and run that at the same time or before and after if you want to, just for comparison. But what's really cool is we'll run a line of dry air. So this is pretty much 0% humidity air. All right. Now, a lot of the times these compounds are water vapor dependent. So we'll want to look, how does water vapor affect this? And so we can run another line of this air through this water. It's this glass tube. It's half full of water, and the air will flow over it and get saturated. So basically the air coming out of this is 100% RH. And so you can kind of mix these two flows to get 0, 10, 50, 100% RH, whatever you want. Then this has a micro syringe filled with your solution. We can inject it using this syringe pump. And, before we do that, we get this level down here, that background level, right? So you before you inject your stuff, you'll get this background level, and you'll subtract that from the signal you get. And that basically background level is just what's going on with nothing in there.
So these additional pieces of equipment you had in the lab, or you had these also on site where you're...
These are in the lab. I made all this. So I wired it up. So the stainless steel tubing, right? So there's a box, and it's basically a big catalytic converter, and it breaks apart all the VOCs of the air coming in, and just with high temperatures. And then so the air coming out has none of the stuff. It's clean zero air is what we call it. And so that was already there. These mass flow controllers were already there. The water humidifying thing was already there. But what I did was this is all Teflon tubing that it's running through. So I put all that together. I had the automatic infusion thing. And this heated stainless steel tubing, I wrapped it with this. It's basically a wire where you plug it in and it gets hot. So I wrapped it with that, and then I covered it. And then I wired that up to a thermocoupler so you can set the temperature, and basically it'll just turn it on and off to maintain the temperature. And so I did all of that, and then of course I made all these solutions just from literature and figuring out how to do it and do it safely.
Right.
And it's just so much trial and error.
Don't want to blow 2 fingers and a thumb off or whatever it was.
No, I do not. So once you start injecting this compound, it volatilizes and heads to the PTRMS. You get this signal up here that's really different from the background signal. And what you want is a big difference between your background level and your signal level, which is really difficult if you got a compound like nitrogen trichloride. Then you can stop the injection, and it'll go back to this low background level. So that's kind of cool. That's the dynamic dilution system. And again, one of the I'm going to try to publish a couple papers off of it, and one of it might be kind of like a technical note is like, hey, look, this is a really inexpensive, fast, reliable way to calibrate your PTRMS, and hopefully it's of enough interest where it'll get published. It'll be kind of nice. And maybe other people will calibrate their PTRMS like that. Maybe my name will show up in some citations somewhere. That'd be kind of neat.
That'd be cool.
Yeah. So to make nitrogen trichloride, you can do this at home. I don't recommend it, but you can.
You can make it at home by peeing in your pool.
Bleach and ammonia.
Bleach and ammonia.
Yeah, you know how they tell you, that's a common thing, is don't mix bleach and ammonia
right.
when you're cleaning, because you're going to make nitrogen trichloride.
Napalm.
I don't think that's what napalm is.
I think it is.
Is it?
Yes.
I'll look into that.
Bleach and ammonia, I believe.
Oh,
is napalm.
yeah, there's definitely another something that goes into it, though.
Yeah, well,
I don't know.
you shouldn't be breathing that in.
No, you shouldn't. So you make all this stuff, but there's kind of the same things that are in swimming pools. So I'm trying to make, I got water, I'm putting these stuff in, I'm trying to make nitrogen trichloride. That's all I want, nitrogen trichloride. That's not all I get. Also, just like in a pool, I've got some hypochlorous acid and hypochlorite from earlier, right? And then also, even at low pHs, because the chloramines in water, they're kind of pH dependent. Even at these low pHs, I'm still going to see some dichloramine. And so I want to get rid of those, obviously, so I could just see nitrogen trichloride. And this is where a lot of my research went into, was using something called UV spectrometry. Spectroscopy, not spectrometry. Spectroscopy. Doesn't make a difference to you, but that's how it is. So basically, we shine UV light through a container holding our solution. Each compound, it will absorb the UV light at different wavelengths. I shot 200 to 400 nanometers at it at one wavelength intervals. And at certain wavelengths, it will absorb that light. And so there will be less light coming through on the other side, and you get this wavy UV spectrum. And you can use that to say, oh, it absorbed this much at this wavelength. I can use this factor to say my concentration was 3 millimolar, right? That's just a concentration that you would find. So I don't want those other things interfering with my UV spec. So what I did is I took carbon tetrachloride, which we were talking earlier. Nitrogen trichloride is not very soluble in water. It's very soluble in carbon tetrachloride. So I'll mix them real good, and then I'll take they'll separate into different layers like water and oil. And I'll take out my carbon tet layer, and then I'd take that to the UV vis and see what kind of numbers I get. I think that's this slide. We use something called, and I didn't ever write anything on my graduation cap, but if there was one thing I was going to write on my graduation cap, it would be A equals ECL, because a guy named Beer and a guy named Lambert came up with it, and it is referred to as Beer's Law. And so if you ever see A equals, it's an epsilon, but we always call it E, A equals ECL on a graduation cap, that is Beer's Law, and that's a very clever, probably chemist that you're looking at. But basically, what's important here is the concentration is equal to that absorbance over this E value. And this E value is something that I got from literature because it's a whole different rodeo to find this stuff. What was really difficult, and there's a whole lot of numbers on this PowerPoint here, but what made it difficult is these asterisks indicate a peak wavelength, right? So we got all these different references, and right here at 336 nanometers, that's where nitrogen trichloride really absorbs, so you get this really strong peak right there. It turns out in water, you get a really strong peak at 336. But in carbon tet, you actually get that really strong peak at 345. So it takes the whole spectrum. It's in the next slide, but it takes the whole spectrum and just moves it a little bit. So it's still the same shape, still the same like height differences, but just shifts it to the right a bit. This isn't something that was shown in literature. This is also something I'm kind of excited about. These guys over here in the 60s used carbon tet, extracted it, ran a UV vis, said, oh, it peaks at 345. Here's that E value that you're supposed to get to get that. And then these guys in the 80s, 90s just looked at the UV vis of the solution in water, and they said, oh, it peaks at 336. Here's that E value you used to find the concentration. Well, I did both. I'm going to go to the next slide here. I did both, and the colored lines are the ones in literature. So aqueous right here, you can see a peak at about 336. And then carbon tetrachloride, you can see a peak more around 345, right? And then here, this dashed line is a solution that I made in carbon tetrachloride that peaks at 345. And this black line is a solution that I made in water that peaks at 336. So I was able to show, hey, look, these guys did it in carbon tet, these guys did it in water, I did it in both, and not only do the spectrums agree with what these two other lab people found, but if you use that E value that each of them said, the concentration comes out to be almost exactly the same. So they were both right, years and miles apart, and I was able to show, hey, look, they were both right, and look, it's the same concentration no matter which way you choose. And that was kind of exciting when I finally figured that out. I was like, oh my gosh, because I did not put it together. It's just so much information, you know?
Sure.
And so when I finally figured out, like, oh, these guys extracted it, and these guys didn't, and they're getting, hey, look, I got different stuff. Hey, look, it all matches. It was just kind of exciting. It was like, guys, look, nail in the coffin. Like, hey, you could do it either way. They're both right. And that was kind of neat to do.
Sure.
Dynamic dilution system. So look, here's a picture of my nitrogen trichloride calibration. You can see this background level, and then all these increases. This is so nice. I didn't have to mess with any flows with my mass flow controllers. All I had to do was go over to my automatic injection machine, and at this first level, I have 74 parts per billion going into the thing, and I'm like, oh, I want my signal to increase a little more. So instead of stopping stuff and adjusting stuff and checking flows, I just went, I'm not going to do it at 1 microliter a minute. I'm going to do it at 2 microliters a minute. I just push a couple buttons, hit start, and bam, you can see it just goes right up. And I'm like, oh, I want to increase the signal a little more, so I bump it up. It's super easy. It's super fast to get this 3-point calibration. Which was kind of neat. But the problem is, see, at the other VOC calibration we're looking at, we were seeing signals of like 600, 700. You can see here I've got signals, and that was at 20 ppb for those compounds. And here I've got signals of like 10 to 60 or 70, and that's at 75 to 150 parts per billion. So you can see this really low signal for nitrogen trichloride, and this is that back reaction with water. Here's another kick in Brian's pants for this whole deal. Pools are humid. Indoor pools are very humid.
Sure.
So I not only need to know what the sensitivity is in dry air, which is what this is a picture of, which I got a sensitivity in dry air of, I want to say, it was 0.2. The theoretical one, like I said earlier, that a lot of people will use, was 8.4. So the big difference. This is why you got to calibrate your instrument.
Right.
I just, for kicks and giggles, put 8.4 in as my sensitivity for my pool data, and it didn't make any sense. Because like I said, we can smell it at 20 ppb, and you could smell it in the pool. It had the level at like less than 5, 10 ppb. And I'm like, that does not make any sort of sense. So the theoretical sensitivity is not correct.
The nose knows.
The nose knows, yeah. And then there's kind of this joke of like tuning your instrument to fit the data, right? You know what I mean? So it's like when I use the theoretical, I'm like, that doesn't look right. I'm not going to use that number sort of thing. Obviously, there's a bunch of other reasons not to, but it was just a kind of a joke.
Right.
So, yeah, here's a few different humidities. There's the one I was looking at, like 10, right? These are all normalized, like 10. We're getting a signal of 10, and the background level is like 1, right? So not a huge difference. You want at least a 3 to 1 a noise to signal ratio, background to signal ratio. At 33% humidity, I'm down to like 3, 4, maybe 5. And then by the time you get to the pool humidity of around 45, I'm getting like 2, right? So I can't calibrate PTRMS at these levels, at these humidities.
Right.
Okay, now I'm stuck again.
Right.
Because it's like, now it's worthless. Because you have to know what it is at those levels. Lucky for us, we've got formaldehyde and hydrogen sulfide. They have similar proton affinity, which means they undergo similar reactions with water. Shown, I think it's just in the next slide here. This is hydrogen sulfide. At the beginning, water vapor, blue line, really high, and then sensitivity really low, like 0.8. we drop the water level down to almost 0, and then the sensitivity jumps way up, I think, to 2.5. So hydrogen sulfide shows this water vapor dependence, hydrogen trichloride shows it, and formaldehyde shows it. The EBO, he did a lot of studies with formaldehyde, and he got a good humidity dependence of it. And so he did 3 studies with multi-point, I think 5-point looks like calibration. And so I fit a line to all 3 of those. I took all 3 lines, I kind of made one, averaged them together into one line, and then I was able to see, okay, 0% humidity, which is what I did for nitrogen trichloride. This is the sensitivity. And then at 45%, where you'd find the pool, it dropped by 3. So you divide it by 3, and that was the difference. And hydrogen sulfide, it did the same thing for me. You divide it by 3 at pool humidity and 0% humidity.
Right. And
so I just applied that factor of 3 to my nitrogen trichloride, and that's what I used for my sensitivity in the pool.
Gotcha.
Yeah. So let's see. Yep. So very low sensitivity, 0.064. Remember, the theoretical was 8.
Right.
So it was tiny.
Right.
And then I think we're finally to the pool. So we're almost done. Home stretch. I went to the Washington State Rec Center pool. The people were super helpful. I got to take a tour. The pool manager, Jared, was very nice. He let me set up in their break room, which is kind of on the other side of this wall here that's shown in the picture. So it's their break room, and I set up there. The maintenance people, they drilled a hole in the wall for me to stick my tube out.
Wow.
Yeah, so you can't really see it, but it's in there. My tube's sticking out of the wall. The pool is gigantic. I think it's like 135,000 gallons with a 10,000 gallon hot tub.
Whoa.
All in the same room. Glass windows everywhere, huge ceilings. I think it was hard to estimate because the ceilings were really tall and then also slanted in some areas. It's really neat if you go there. You can go upstairs and look out into the pool while you're on like the ellipticals and stuff. Oh, it's kind of neat. But the room was, I estimated it at like 200,000 cubic feet, which is a big space. And their HVAC system, the little information I did get was that it can pump out 41,000 cubic feet per minute, which is insane.
That's a
but
lot.
It makes sense because I looked into the Washington State regulations, and for indoor pools, they recommend about 6 air changes per hour. And so that would be the system running at 50% at all times. It doesn't. I'm sure it kicks on and off. But that would be 6 air changes per hour. Yeah. So at the WSU pool, here's a bunch of compounds that I was looking at: formaldehyde, methanol, acetonitrile. I'll talk about the other compounds that we saw. And here's a nice picture of nitrogen trichloride and people in the pool, right? Because that's one of the things. If you can't take a lot of data points, how are you supposed to match up people in the pool, which the lifeguards took count, and that was one thing Jared was nice enough to give me, was all the pool counts, how many people were in the hot tub, how many people were in the pool, and it was an hourly average. So 6 to 7 today, there were 5 people in the pool, 4 people in the hot tub, right?
Right.
So I was able to put that on behind my data, and as you can see in the picture, if you're looking, you've got this pool person count, the red and black here. This is a pool and hot tub. And then you got these nitrogen trichloride levels. And so when the pool is open, you see the levels go up and down.
Right.
With people. And you got a lot of people, you get higher levels. You get little people, you get real low levels. And it's really neat. One thing that I forgot to mention when we were looking at all the current data, no, I think I mentioned it, 0 to 350 parts per billion. The WSU pool looked like it was a tad high, tad higher than most of the other stuff. Not out of the realm. Again, there are a couple steps. The PTRMS could be calibrated maybe better than what I did, and you can get a more realistic number, but I feel pretty confident in this. And the average, I think, was about 114 parts per billion for the 13 days I was there. The max, I think, was 254 255, and then the lowest level I saw was about 32 parts per billion. Yeah. Let's see here. From those studies earlier, the amount that is said to start causing irritation would be 100 parts per billion. Some people say it's closer to 50, but as we can see, we're just right at that level to where you're swimming and you're a bit sensitive. You might be noticing some throat irritation, or maybe your eyes are real red or something.
Right.
Yeah. Let's see. So that was kind of the culmination of this whole thing, and it was really cool. There's no other graphs like this that show this level of, I mean, this is 13 days of stuff.
Right.
This is something called a diel graph. So it takes every weekday, every Monday, Tuesday, Wednesday, Thursday. So there's 2 of each. Yeah. Except for a Friday, I think. Depends on what day I started. And it takes all of those days at the certain time, and it averages them for all those days. So this is, on average, what you can expect at a certain time in the pool. And you can see it just follows this bather load pretty closely. A nitrogen trichloride was the highest thing I measured by far at around 100 parts per billion. The next closest things were acetaldehyde, isoprene, methanol, and acetone. Isoprene was really cool because that's something that's released from your breath when you're exercising. So the idea is, if you've got a bunch of people exercising, they're releasing isoprene from their breath. If you're releasing isoprene from your breath, you're probably sweating. If you're sweating and in the pool, you're going to be creating nitrogen trichloride. And you can see it's this dotted line. They really follow quite closely together. The nitrogen trichloride and isoprene levels.
That's pretty
And
cool.
actually, so does acetaldehyde. It kind of follows that same trend as well. I'm not 100% sure. I'd need to look into it more. But what is really cool is methanol and acetone, they don't follow the trend. They kind of do their own deal. And so it just kind of goes to show, hey, maybe I was right. Maybe isoprene and nitrogen trichloride are kind of similar to each other as far as when and how they're getting released.
Gotcha.
So that was that was neat to see. It was just kind of a fun study. We were talking about, okay, what happens when it leaves the pool after, it leaves the building. This is a neat graph. This is what, as far as art goes, I would frame this, put it on the wall. It looks like an abstract painting of some sort.
Kind of does.
This
Looks like it might be the design on like a one-off LaCroix.
Yeah, there you go. Exactly. or a shitty Patagonia hat or something. But basically what this shows is this yellow bit, the bottom is wavelength. So this is how many photons of each wavelength are going to hit the ground in Pullman on a sunny day in September. This is actually a measurement. I got it from NCAR, National Center for Atmospheric Research, I think. And I used that number and the absorbance cross-section for gaseous nitrogen trichloride that was reported. And I got this, it's called a photo dissociation rate constant. And it's basically, you can use this to say how long, if nitrogen trichloride is in the air, how long is it going to take for it to be broken apart by the same light that you'd get a sunburn with. And I found that in September, for one day in September, best case, the shortest time that it would be around would be about 2 hours. It goes all the way up to like 16 January, February, and all the way down to 1 or 2 hours in the summer, just because we're getting more light. And then that would be, those are kind of best case scenarios. It could be longer than that. Yeah. And then that's this one here, so you see the lifetime going. I think that's about it. So, have I convinced you? Don't pee in the pool. You're gonna breathe this stuff in.
Well, I think maybe you ought to not pee in the pool just because it's gross. But now we all know it's also something that you shouldn't breathe.
No, it's gross for a reason you wouldn't even think of, right? You think you're swimming through people's pee. Actually, almost as soon as you pee in the pool, all that stuff gets broken down into other things.
You're breathing the pee.
it's not pee at that point. But yeah, it's not that you're swimming through other people's stuff, but you're breathing it in, and that's gonna cause some stuff. And I can't remember what I was listening to or looking at, but they were talking about how with lifeguards, not lifeguards, Olympic swimmers, it's a common thing that they just pee in the pool. They just talk about it. I think Michael Phelps in an interview.
They're just so focused and don't want to get out.
They don't want to get out of the pool, so they all just pee in the pool. And then they breathe it in, and then years down the road, they're going to have all these problems. And that's something that everyone knows. You're supposed to take a shower and don't pee in the pool. No one really knows why, right? Like I didn't before I started this. You you weren't supposed to. Yeah. Or no, hey, I don't want to swim in the pee, even though that's not really what you're doing. There is a very good reason not to pee in the pool, and it's because you're going to breathe it in or other people are going to breathe it in, and it's going to create a nasty atmosphere for everybody. Yeah.
There it is, folks. Do not pee in the pool. Brian, we wish you the best of luck in defending. I think they will. We wish you the best of luck in defending your thesis.
Yeah, this comes with like a 70-something page paper
I can
as well.
imagine. Yeah. Yeah.
A little more in depth, and I left out a lot of the super sciencey parts.
Right. Yeah, but it's been a lot of work up to this point, I imagine, and I bet you feel really good to have this done and sort of out of the way.
Yes, as I'm checking off the last few things on my list, it just feels so good to be done. I've been in school since 2014.
Right.
I started online college. Let's see. I met Caitlin. We moved to Spokane from North Carolina because she got into Gonzaga for her school counselor's master program. Mm-hmm. And so I just got a job working at Pizza Hut. Mm-hmm. And she was about finishing up with her degree, and she's like, well, why don't you just do some online courses? Because I thought, I don't want to work at Pizza Hut forever.
Right.
And so I thought, maybe I'll do nursing. That seems like something I could do. Mm-hmm. And so I started taking some courses online at Spokane Community College. And then I think I did that for maybe a year. Mm-hmm. I think it was, they're on the quarter system, so who knows how many quarters it was. And then when we moved back home, I transferred to Walla Walla Community College and finished up there. It was there where I decided that nursing sounded very hard. And it is. It's got to be one of the hardest jobs ever. Mm-hmm. I think I heard something on NPR where more nurses have injuries than construction workers.
Oh, wow.
Like, it's got a higher injury rate. And I think it's from lifting some hefty people.
Yeah.
Mostly.
Yeah, I imagine you get all kinds of problems with your joints and your feet.
Yeah.
A lot of plantar fasciitis.
Yeah, yeah. And so nursing just kind of went off the table then, and that's where I discovered chemistry and how much I really like chemistry. But yeah, been in school since 2014. I'm done.
Yep.
I'm done. I don't want to do it anymore. Writing is not my favorite thing. Mm-hmm. So it's like pulling teeth to get me to write something I don't care about. Mm-hmm. But I'm happy that I did it. I'm glad that it's over. Mm-hmm. But yeah, man. Whoo! Feel like I just talked a whole bunch. Cool. Well, thanks for listening, those of you that remain.
We took a bit of a trip outside of the valley, but I guess not necessarily if you have an indoor pool. It was pertinent information.
Well, the aquatic center, right?
The aquatic center.
It applies to the aquatic center. And next time you go into pool and you smell that and you smell that chlorine smell,
get out.
It's nitrogen trichloride. Don't get out. You're fine. Adcope. Gosh, I don't know if anybody remembers Adcope.
Well, it's snapped now.
Well, no, back when it was, and it wasn't even at the end of Adcope. I think they fixed it, but I'm talking about like mid 2000s Adcope. That pool in there was horrible. Mm-hmm. And I imagine that the levels of nitrogen trichloride were at least double of what I saw at the WSU pool. It was so bad. And it's kind of nice relating that back to what I'm looking at now and being like, oh, that's what that was. That was nitrogen trichloride. So yeah, that's what the pool smell is. Don't be in the pool. So yeah, now we just have to figure out what we're going to do next week.
Ooh, next week.
Next week, everybody. Drew, why don't you take half a minute and your girlfriend, Rachel, hi, Rachel, bought a house.
She did.
And you guys are moving into that house.
Yeah, we're working on it now. We're knocking down some drywall, and I spent much of the day sanding the hardwood in there. Basically, the whole upstairs is hardwood, so sanded that down, and it's a lot of work, but it's going to be great when we get it fixed up and can move in.
Heck yeah.
Yeah.
Well, again, thank you, everybody. I promise we won't do this again for a while. No, I had fun. I think it was enjoyable.
You can hang up your student hat for now.
I can hang up my student hat. Yes. All right. Well, anything else?
I think that's it. Thanks for listening, everyone.
All right. I just want to say, live your life to the fullest. I'm pulling a Henry Zabrowski here. Laugh. No, I'm just No, let's see. I just want everyone to know, if you're feeling a little alone during this time, I'm giving you a virtual hug right now.
There you go.
I'm wrapping my voice around your earlobes, and I just want you to feel how much I love and appreciate you guys that listen to the show.
Especially our Patreon listeners.
We got some new Patreon subscriber. Thank you to the Funks, baby. Yes.
We got the funk.
We got it. Yes. So we really appreciate our Patreon subscribers. And, that's right. I've got like a full Patreon episode that I'm going to put out later this week, probably after Wednesday when I defend this thing. But I think by the end of this week, I'm going to have a Patreon episode out that's just for Patreon listeners.
Awesome.
And we'll hopefully do some more of those too. So there is a good reason to subscribe.
Cool.
All right. That's it. I'm done.
See you, everyone.
Cool.
Sweet.
Woo! I feel like I talked my head off.
That's good, though.